Good afternoon everyone, and welcome back to another video on my channel. Today I'm going to go through the proof of the secretary problem. So if you remember, the secretary problem had this stopping method solution where you had to kind of first get a taste of what the kind of applicants were like, and then interview our applicants out of N, and then what you would do is reject all those applicants, and then afterwards you'd also pick out the M, which would be the max, the best applicant within the first R that you picked, and then you would pick the first applicant that was better, and that allowed you to get a better kind of idea of kind of what the applicants were like, instead of just going randomly and picking a random applicant out of N, which would give you 1 out of N chances, which is quite low. So we can do better, right? So now I'm going to show you how to actually obtain that R. So what happens is we have all our applicants in here, and we have a cutoff point R here, and we interview this one, pick out which one's the best, and then go interview these ones, and then the first one that is better than this M, will pick him or her. And if unfortunately there is no one that's better than this applicant M, we'll just be left with no choice but to pick the last one. And this is actually quite interesting because to be fair, we can actually look at examples. For example, if we have only one applicant, we'd have a choice, right? So we have 100% chance of picking this applicant, since we don't really have a choice. This is not very interesting. A more interesting case would be 2. So if we have applicants, let's call them 1, 2, with 2 being the best and 1 being a little worse, then we have a 50-50 chance of picking this one and a 50-50 of picking this one. So still not that interesting. Where the algorithm does become interesting is with 3 people, which is actually quite a good example, because that way you can pretty much see what I mean. So we have 1, 2, 3. We shall arbitrarily assume that 3 is the best, with 1 being the worst and 2 being in the middle. And what we're going to do, we're going to first look at the probability of picking number 3 if we just go in blindly. So obviously it's going to be a third, since we have a 1 out of 3 chances of picking 3. However, if you actually do apply the method, the stopping method, you'll see, and I shall show you that actually you can increase your chances, right? So what are the possible ways that the applicants come to get interviewed? Well, they could come 1, 2, and 3, as right here, or they could go 1, 3, and 2. They could go 2, 1, 3, 2, 3, 1, and then finally 3, 1, 2, and then 3, 2, 1. And if we use our technique, we can see that, right? So in the first case, so we look at number 1, we reject them, and then we look at 2, is 2 better than 1? And yes, it is, so we hire 2. And unfortunately, we miss out on 3, and this one ends in a loss for us. If we look at this one, we can interview 1, reject him or her, and then hire 3, and in this case it would work, so we would actually get a winner in this one. Same again on number 3, so interview 2, reject him. Is 1 better than 2? It is not, so in this case we would hire 3. Once again, we would be good here. So reject 2, is 3 better than 2? It is, so we win in this one. And then here we reject 3 in both cases, so we lose. So we can actually see in 3 out of 6 cases, we get actually a win compared to here, which we only get in 1 out of 3 cases. So we actually improved our chances from 1/3 to a half, which is about 17%. So this is actually quite an interesting case. Right, so now let's actually go through the maths. So I'm going to write down the number of applicants. So first I'm going to say, right, so we're going to assume, so the conditions, assume n applicants, right? So this number is known beforehand. So we will use the stopping method, a bunch of names like the 1/u or whatever, method with cutoff point R, so we will hire all the applicants from 1 to R included, just to make it easier. And then we will reject all the applicants from 1 to R, and then we will apply the method on the R plus 1 to N. Next, we can assume. All right, let's call him John. Be the best applicant. And then what we're going to do is he's going to be at position I. So we're just going to write down at position I, which is obviously got to be smaller or equal to N. And right, so John's got to be position I, and our goal will be to find and hire I, right? So if we don't hire this person at number I, so I'm going to refer to John as candidate I from now on, just like referring to his position. And if we don't hire I, then we've lost, and if we do, we win, right? And our goal is to maximize our chances of hiring I. So for example, I'm just going to draw a little line. I'm going to just, to make it easier to understand. We have n applicants, so this is going to be 1, this is going to be 2. We're going to have our cutoff point R, so we're going to reject all these. And so we're going to look at the first one that's better than the maximum of these. So let's let M equals the max of the applicants, so within 1 to R. And there we go. So we will hire the first one that is better than M. Cool. So first, what we need to do is to find information about this R, which is the entire point of this video, to know what R is, or R should be, to maximize our chances. We need to look at when the algorithm would succeed or when the algorithm will fail, right? So obviously, if we look at the first case, the algorithm would fail. When would it fail? Well, obviously, if our applicant I were to be within this kind of region, right? So if I is from 1 to N, so I is in the section 1 to R, then obviously we would reject him and not know it, and in this case we would fail. So pretty much we have to kind of assume that I shall be in this second section. Obviously they won't always be, but that's unfortunately is the nature of the business. So second way it could fail would be literally, so we will assume that I is not within, so 1 to R. So now we are working with an I after R. And however, the algorithm could still fail. And how would it fail? It would fail when the maximum. So for example, so we have our M here, and if we have a candidate here that's better than M, so let's call it candidate X, and if X is better than M, we are going to hire this certain X, and we are not even going to get onto our candidate I, which is like the best candidate, right? So if X is better than M, unfortunately we will not get the correct candidate. So how could we write that down mathematically? We could literally think about it and then write down that we need the maximum value. So we need M. Let me just write down. So actually, no, let's leave it. So max between 1 and I, not included, has got to be within the position 1 and R. This way, we will look at the maximum, we will reject him or her, and then afterwards, any candidate here will be worse than the maximum, right, by definition. So we are left with two conditions that if we want our algorithm to succeed, we need I to be greater than, so to succeed, we need I to be greater than R, naturally. And we also need max of 1 to I to be smaller or equal to R. Right, so what we're going to do now is write down two events. So event A and event B. And I'm going to call event A the event that we pick the best candidate. So event we pick candidate. Actually, let me just write it probably the best candidate. The best candidate. And now we're going to call event B that the event, actually let's call it B I. This is going to be the event the best candidate is at position I, right? And now what we can write down is so the probability that of A, what's that going to be equal to? It's going to be equal to obviously the sum. So the sum of the probabilities that like we pick, so that the best candidate is, for example, at position 1, and that afterwards we actually pick this candidate at position 1, right? So it's going to be probability candidate is a position 1 times the probability of a higher position 1 plus the probability the best candidate is a position 2 times the probability of higher position 2, so on and so forth until position n. So what happens here is it's going to be the sum from I equals 1 to n of the probability that we pick the best candidate. So we pick the best candidate given that the candidate is at position I. So the best candidate is a position I, and then times by the probability that the candidate is already at position I, right? So we are left with this. We can see pretty easily that this probability is simply 1 over n. Simply there are n possibilities and possible kind of places where the best candidate can be. So this is pretty simple and a given. So we are left with probability of A is equal to 1 over n times by sum from I equals 1 to n times P A given BI, right? And now what we can see is obviously from our tactic, we can see that we are going to reject every single one of these candidates. So what's going to happen is that if this candidate I is within 1 and R, he's going to be rejected, unfortunately. So we can write that down. Actually, let me write it down clearly. So I equals 1 to R times the probability of A given BI. I'm just splitting the probabilities at the moment. So, sorry, the sums. I equals R plus 1 to N times the probability that A given BI, right? And what happens is now this is equal to 0, simply by definition of our tactic. So we are left with 1 over N times by I equals R plus 1 to N P of A given BI. Right, so we look at our conditions. We've already used the first condition in determining that this was 0. And what we do with the second condition, we are simply told, we have worked out that the maximum value between I minus 1 and 1 has got to be within the first R, right? So how do we write that down? We pretty much write down, so actually let me write that down properly. So these are going to be the first R, and then our I is assumed to be in this position now, since we are looking at the I's from R plus 1 to N. So our I is going to be beyond R. And what we do now is we look at the probability that the best, so let M dash be the best candidate in the range, so from 1 to I minus 1, so from this one to that one. And we want this m dash to be within the first r. So we want m dash here, right? So for m dash to be within 1 and r, so what's the probability of that? So probability, so we need, so probability of this, let's call it event C. Probability of C is simply equal to, pretty easily, so we can see it's r divided by r minus 1, since every single spot in these has got the same probability. So it's this simple, and we can rewrite this star as equal to 1 over n times by the I equals r plus 1 to n of r over I minus 1. And we can rewrite that simply, since r does not depend on anything. R divided by n equal to the sum from I equals r plus 1 to n of 1 over I minus 1. So this simple. Right, so we have this this little sum right here, and we want to kind of make it a little bit more concrete. How do we do that? We can notice that this is actually a Riemann sum. It's pretty simple. So first of all, we simplify this a little bit more by changing the index. So let's just change it to I dash, and we'll notice that we get I equals from r to I minus 1. Right. This is a simple change of index. If you don't understand, write in the comments. But this is pretty much the same. It's just written a bit simpler. And what we do now is simply, let's see. Oh, sorry. Right. There we go. This is simple now. What we do now is we notice this is actually a Riemann sum, and we can actually rewrite that almost as an integral, right? So the integral between r and n of 1 over I di. And how do we know that? It's because if we look at what the sum really represents, 1 over I, so this sum really represents these. Right, and you go what I mean. And the integral will actually find the exact area here. Right, so this is pretty much an approximation that we can rewrite. And this is equal to, in turn, so what's the integral of 1 over something? It's, as we all know, it's ln, so the natural log. So it's natural log of I between r and n. And we rewrite that as r over n times by natural log of n minus natural log of r. Let's not forget the brackets, and then rewrite that in turn. If you know your laws or logs, ln of n over r. Actually, I can write that a bit better. So ln of n over r, right? And so we have this expression, and we want to optimize this. So that means find the value of r that actually makes let's call it star the greatest, right? Since this is our kind of formula for our expression for the results. So for like the probability that we get the correct person I is given by this expression, and so we want this probability to be the highest. So we want to see how what values of r will give this highest value. And how do we optimize? How? Well, we differentiate and set to 0. So this is back in differentiate. This is back to kind of GCSE further maths or whatever. You differentiate. How do you differentiate? So you have d of this double star by dr is equal to r over n, ln of n over r. So actually, sorry, d of r over n times dr over dr. Right, and this looks a bit complicated, so we just let, I don't know, we can let x equals r over n, in which case we get that this formula here is equal to d x ln of x, sorry, ln of 1 over x, sorry, ln of 1 over x by dx. If you know your logs, rules of logs, you know that ln of 1 over something is simply minus ln of that something. So we get minus x ln of x. So we want to differentiate this certain minus x ln of x. So we use product rule. And what does that give us? So we hold, differentiate, hold. So we get minus 1 times by ln of x plus, we hold minus x and then differentiate ln of x, which simply gives us 1 over x. So we get minus ln x plus minus x of x, so minus 1, which gives us minus 1 plus ln x. Now, right, to get the maximum, we set it equal to 0, and that gives us 1 plus ln of x is equal to 0. ln of x is equal to minus 1. Let me write that properly, and then we get in turn x is equal to e to the minus 1, which is equal to 1 over e. So we get our maximum value when our x is equal to 1 over e. What did we set x to? We set x to r over n. So that means that r over n is equal to 1 over e, which gives us that, so we want our r, so n is fixed, so r is equal to n over e. Right, and you have seen now, as I said in the last video, that this maximum value is found at n over e. And it is indeed the case, and I have proved so. So we can literally pretty much say, for example, we can plug in some values. So if n is equal to 100, for example, then we get r is equal to 100 over e, which is 37, about 37. And there we go. What I'm going to do now is I'm going to program it really quickly. So I'm going to use the code that I used in the last video and add to it to show you, like, kind of to go through these different values of r and actually give you like output, which like the probability of finding this best candidate. And what we're going to see is that it indeed approaches this 37. So when this best value is at 37, when we pick 37 as our cutoff point, then we definitely get the best probability. Right, so now I'm going to show you the code. So this code, I explained it all in the last video. So I wrote it and also explained each line previously. If you want to watch that, you're more than welcome to do so. Now, what we are going to do now is going to literally just add a new function to compute. I'm just going to write it down. Compute probabilities for different cutoff values. Go on. So, and right. And what we're going to do is create a new function called define compute probabilities, and give it two attributes, so number of candidates, which we have already kind of created here, and number of tries. So we'll be able to kind of influence this function and give it a certain number of candidates and a certain number of tries. And it's obviously going to call this interview function right now, so a bit later on. Right, what we're going to do, create an array called probabilities, make it empty, and now for cutoff, we're going to create a for loop that cycles through each and every kind of value of n. So for example, so here for example, we can go for, as I showed you, like here I've already kind of run it once. I'm just going to explain it all. And what happens is, so we're going to go through 2, 3, 4, 5 with like 100 values, and this is going to kind of allow us to see every probability. So for cutoff number in range 2 and number of candidates, there we go, plus 1. So for example, so we're going to cycle through each probability. We can't go use 1. Why? Because actually starting from 2 would give an empty list, and it wouldn't work. I tried earlier, but what happens with 1 candidate is you pick him or her anyway, and there's no fun in anything, right? So number of candidates plus 1, and we're gonna have prob. We're gonna create this prob list of probs that we're gonna append to the array of probabilities is equal to interview. So no candidates, and then let me see, no candidates, cut off number, num tries, cut off number and num tries. There we go. So and now we're going to append this prob to probabilities. So probabilities are append. So we're going to append cut off number and prob, and we're just going to have to now just return the probabilities. So this array, we'll return this array so that we can actually access outside the function. And now we're running the simulation. So for example, we can start small. In this case, I used 100 candidates and 100 tries. So let's do that. No candidates is equal to 100. No tries is equal to. Oops, I said it. Num tries would help if I were consistent, wouldn't it? 100. And now we are going to create this new results is equal to compute probabilities. Come on, yeah, there we go. With no candidates and no tries, and num tries. Sorry, there we go. And right, oops. And now all we need to do is display the results. So displaying the results, and pretty much we're going to create another for loop to display them. For cutoff prob in results, pretty much it's a fancy for loop. Yeah, just like to give us what we want. Cut off print, we're going to print cut off double dot, and then in there we go, cut off. I'm trying to remember how these special strings go. Comma win probability. Yeah, it's pretty much how I wrote this, isn't it? Oops. And then once again, these curly brackets, prob double colon 0.2f, and all we need now is the percentage outside. There we go. Right, and this would have been important, wouldn't it? And there we go. This should be it. So we've created a new function that pretty much uses a for loop, uses this def interview every time, and returns this probability array. And now we run this and we output the results with the probabilities. So this should be all right. With 100 candidates and 100 tries each. We won't get the perfect kind of line for this. We would have to use 1,000 candidates. Right, so we got our answer. We can see here. So if we cut off at 2 candidates, we get 8%. So 8% of the time we actually get the correct probability with our method. And this probability increases, 46, 43. You can tell there's some like 35 here, but like 100 candidates is not that much. And you can tell when we get around 37% that we indeed get the highest values. This is not very accurate, so what we can do, we can instead use 1,000 tries with still 100 candidates, and this might take a while, so I'll just cut the video now and then yeah. Right, so we can see now with 1,000 tries, the probabilities will kind of behave a bit more. So before 37, we have small probabilities and increases up until here at 37 we get 40.3, and afterwards it starts to come back down. So indeed, we do get, actually, the maths does kind of work. It does work, and fortunately so. And we can see actually that this is indeed quite a nice kind of like method for quite a difficult problem, because obviously it's quite abstract, isn't it? So you have 100 random candidates, and then you just got to pick a certain one and hope it's the best. Now this method will not really kind of be applicable in real life. Why? Because one, you don't always know the number of candidates you have. Sure, sometimes you do, and also you don't always have to kind of reject them immediately. And finally, yeah, well, it's a bit kind of, it's relies on a bunch of kind of assumptions that are not really kind of real life assumptions. I'm using kind of a lot, but that's pretty much it. It wouldn't really be applicable, but it's actually really interesting, and there are a lot of things that can pretty much come out of this. Right, well, thank you very much for listening. I shall see you guys in the next videos. If you have any questions, just feel free to ask me. Bye bye.